进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学》的数学原理。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。
Hello, everyone. Welcome again to our CHASSpark OTF ISAC online seminar series. And today, it is our great pleasure to have Professor Yong Zheng from Southeast University to give us a talk on rethinking waveform 6G communications and sensing, delay-Doppler alignment modulation. Please allow me to quickly give a brief introduction of Professor Zheng. Professor Zheng is an IEEE Fellow, Young Chief Professor of Southeast University and Purple Mountain Laboratory, Nanjing, China. He received the Bachelor of Engineering first-class honors and the PhD degrees from Nanyang Technological University, NTU, Singapore. From 2013 to 2018, he was a research fellow and a senior research fellow at the NUS, Singapore. From 2018 to 2019, he was a lecturer at the University of Sydney, Australia. Professor Zheng was listed as the highly cited researchers for 7 consecutive years. AI 2000, the most influential scholars in the field of Internet of Things for 4 consecutive years. Stanford top 2 scientists in the world lifetime influence. Very impressive. Professor Zheng is a recipient of the ARC Discovery Early Career Research Award, DECRA, IEEE Communications Society Asian Pacific Outstanding Young Researcher Award, and win 10 international and domestic best paper awards, including the prestigious IEEE Marconi Award, Heinrich Hertz Award, etc. Professor Zheng proposed the concept of a channel knowledge map and the delay-Doppler alignment modulation transmission methods. His work has been cited by more than 39,000 times. He served on the editorial board of ICI journals such as IEEE Transactions on Communications, IEEE Transactions on Mobile Computing, and IEEE Communication Letters, and the leading guest editor of journals including IEEE ComMag, Wireless ComMag, China Communications, and Science, China Information Science. Professor Zheng was evaluated to IEEE Fellow for contributions to UAV communications and the wireless power transfer. So without further ado, please join me to welcome Professor Zheng for today's talk. Thank you.
Okay. Yeah, thank you, Shan-Yang, for the kind introduction and for the invitation. Let me share my screen here.
Mm-hmm.
Okay, so hello everyone. Thank you for joining us today. And of course, I would like to thank CHASSpark for giving us this opportunity. And also thank you.
Professor Zheng, would you like to give the full screen for the presentation? We can currently only see the PowerPoint.
Yeah, I can see there is some delay. Sorry.
That's great. Thank you.
Okay. Yes. So is it okay now?
Yes, it's good. Thank you.
Delay. Yeah. Sorry. Yeah. So I would like to take this opportunity to introduce the concept of delayed Doppler alignment modulation, or DDAM, from the waveform perspective. So I will first briefly review the so-called inter-symbol interference mitigation techniques, and then we'll introduce the concept of delay alignment modulation. And first, I will introduce the DAM in the single carrier scenario. And then I will introduce DAM with OFDM. So how DAM can be integrated with multi-carrier communications. And hybrid beamforming for DAM, because we need to use large antennas. So hybrid beamforming is one of the main techniques we need to consider for DAM. And then we will also introduce a multi-user DAM. In the multi-user scenario, how do we apply the concept? And after that, we will introduce the more general concept by also considering the Doppler alignment. So we have the DDAM. And we have also some very preliminary prototyping and experimental results. And also how can we apply DAM for ISAC? Okay, so the evolution of wireless communications actually involve how we, one of the major issues is how do we deal with the inter-symbol interference, or ISI. So in 2G, when the data rate is not very large, we usually use the channel equalization. So it can be applied at either the transmitter, so we can have the pre-equalization, or at the receiver. So we have the post-equalization. And for 3G, we have the widespread or spread spectrum. For example, for WCDMA, we may use the spread spectrum technology to deal with the multi-path or inter-symbol interference. And in 4G and 5G, we have the very successful multi-carrier communications, especially OFDM. But for 6G, actually, do we have any new possibilities for the waveforms for 6G? During the past few years, there are different studies. For example, a very famous study is on OTFS. Of course, recently, we also have the AFDM and the IFDM. But these different technologies have the pros and cons. For example, even for the very successful OFDM, the main issue is the high PAPR, the peak to average power ratio. And it has the OOB issue, and as well as the vulnerability for carrier frequency offset. So actually, recently, 3GPP has already discussed the possible waveforms for 6G. But unfortunately, I think the main waveform is still OFDM. Maybe there are different reasons. So the baseline waveform for downlink is still CP-OFDM. And for uplink, we may have the CP-OFDM and also the DFT-SOFDM. Other waveforms are considered, but they are not actually given the highest priority. The main consideration is that we may further consider some techniques to enhance the OFDM waveforms. For example, how do we further reduce the PAPR? And actually, how do we perform the dynamic waveform switching and so on and so forth? So in 2026, this year, we propose, actually, we have one tutorial paper called the tutorial on MIMO OFDM ISAC. So from the ISAC perspective, how do we apply the MIMO OFDM? Because now OFDM is will be still the main waveform for 6G. But of course, we can still try to enhance the different performances for OFDM. So if we come back to the basics of OFDM, let's consider this fundamental question. If we want to achieve the so-called extremely low PAPR and extremely low CPU overhead. So what kind of condition, what kind of criterion do we need? So if we consider the spectrum efficiency or the CPU overhead, we have this very single number rho, which depends on the symbol duration without considering the CP, as well as the symbol duration considering the CP. So look at the symbol duration TS that will carry the useful data. But we need to insert a CP so that we can remove the inter-symbol interference or inter-block interference. So of course, if we want to enhance our spectrum efficiency, we need this ratio to be close to 1 as much as possible. So that basically means that we want our CP duration to be very small. So let's say if we have certain threshold for this ratio, let's say 90% or 99%, then it basically means that the CP duration should be very small as compared to the symbol duration. So this is how we can use a very simple number, which is to denote the spectrum efficiency. But on the other hand, if we want to also reduce the PAPR, we know that for OFDM, the PAPR actually depends on the number of subcarriers. So let's say if we want our PAPR to be smaller than certain threshold, then we can restrict the number of subcarriers. So we have another requirement K for the number of subcarriers. But if we further consider how these two criteria are related to the channel itself, with very simple derivation, we find that in order to achieve the desired spectrum efficiency in terms of ZTH, and also the PAPR in terms of the number of subcarriers, we have actually some criterion or some requirements for the channel delay and the Doppler spreads. So basically, the delay spread should be no greater than certain threshold. It depends on these two parameters, ZTH and KTH. And also, of course, the Doppler spread should be much smaller than the subcarrier spacing, so that we do not have the intercarrier interference. So we can derive these two conditions based on the fundamentals of the parameter selection for OFDM. For example, if we have the system bandwidth given by B, then the subcarrier spacing depends on how many subcarriers we have, and also the CP duration should be no smaller than the channel delay spread. So with very simple calculation, we can find these two criteria for the delay spread and the Doppler spread of the channel, so that we can achieve the desired spectrum efficiency in terms of the ZTH and also the PAPR in terms of the number of subcarriers. So we can actually plot the delay spread and the Doppler spread within a figure. So let's say if we want to achieve the spectrum efficiency of 90% or ZTH is 0.9, so that basically means that 90% of the time should be used to transmit new data, and only 10% for CP. So we can have this feasibility region for the channel delay spread and the Doppler spread. But if we further increase the spectrum efficiency to 99% or ZTH to be 0.99, then the feasibility region is reduced. So that basically means that in many practical scenarios where we have the large channel delay spread and the Doppler spread, it is impossible to push our CP overhead to be an extremely low value, and also to simultaneously to push the number of subcarriers or PAPR to an extremely low value. For example, if we want to achieve a so-called extreme OFDM with ZTH to approach to 1 and the number of subcarriers to approach to 1. So this basically reduces to the single carrier. So this will require that our delay spread to approach to 0. But of course, this is not possible in many practical scenarios. So the fundamental question we ask is, for practical time frequency double selective feeding channel, is it possible that we have some OFDM or multi-carrier system, but we can still achieve the extremely low PAPR and CP overhead? So based on what we discussed so far, this is possible only if we can reduce the channel delay spread and the Doppler spread. So the question reduces to under what conditions that we can manipulate our channel delay and the Doppler spread. So this actually motivates our technique, so-called delay Doppler alignment modulation. But before we discuss the more general DDAM, let's first discuss the simpler DAM or delay alignment modulation. So why DAM becomes possible in 6G but not before 6G? Based on our understanding, at least 3 major trends for 6G will motivate, will push the DAM, will drive the DAM to be possible. So the first trend is that for 6G and even beyond 6G, we will have more antennas. So in 5G, we have massive MIMO with 64 or 128 antennas. But now for 6G, we're likely to further increase the number of antennas from massive MIMO to extremely large-scale MIMO, XL MIMO. So this will basically mean that we will have super spatial resolution. And another trend is that for 6G, we will move to higher frequency bands, let's say to millimeter wave or even terahertz. So as the frequency goes higher, we have the so-called multipath sparsity. So we do not have so many multipaths as in the conventional sub-6G. So the number of multipaths or the number of significant paths may be limited. For example, 2 or 3 multipaths. So another trend is that 6G will integrate localization, sensing, and communication. So this means that different from our traditional 5G or beyond before 5G systems, we usually want to only estimate the channel in the time frequency domain. But for sensing, we really want to extract the path information embedded in the channel. So we have the multipath resolvability capability in ISAC. So these 3 trends actually give us the new opportunities for inter-symbol interference mitigation. So if we can have a super spatial resolution, that basically means that we can resolve or distinguish more paths in the spatial domain. And if we have the multipath sparsity, it means that we can simply compensate the delay and the Doppler of each multipath after we resolve them in the spatial domain. And so delay alignment modulation actually is based on 2 key ideas. The first one is that we need to have a path-based delay and delay pre and post compensation. So if we can estimate the delay of the multipath, we can simply apply the compensation either at the transmitter or the receiver. But this is possible. This is possible only if we can resolve the multipath in certain domain, let's say in the spatial domain, so that we can decouple the multipath in the spatial domain. In that case, if we apply the compensation for one path, we will not affect the delay or Doppler of the other path. So this is very important, and it is why this kind of concept is only possible in 6G, but not in 2G or 3G, because we do not have so much degree of freedom in the spatial domain. So let's consider a concrete example. Let's say here we have 5 multipath clusters. If we plot the delay and the Doppler of all the 5 clusters, we can find that we can still have a very large delay spread and the Doppler spread, although we have the sparsity in the delay and Doppler domain, because the minimum and the maximum delay and the minimum and maximum Doppler may be quite large. So the delay spread and Doppler spread can be still large. So if we plot the corresponding channel in the time and frequency domain, we found that it is still a frequency selective and also time variant. But if we further plot the delay Doppler and angular domain channel, we found that we have the additional resolution in the spatial domain. So let's say if we consider the angular domain, the different clusters may belong to different angles. So this basically shows that if we can exploit this spatial domain degree of freedom to decouple the different clusters, then all the clusters we can apply the independent delay and Doppler compensation. So we can reduce the delay and Doppler spread. This is a basic idea for delay Doppler elemental modulation. So how do we achieve this mathematically? If we consider this very simple scenario, let's say the single user and the massive MIMO scenario, the transmitter has a very large antenna. And let's say in this case, we consider the very simple scenario that the receiver has only one single antenna. But there are many different, there are multipaths. Here we show 3 different multipaths. So the paths, the different multipaths may have the same delay or similar angular resolution or similar angles. But if we express the channel impulse response, we find that let's say the channel includes L multipath, and each path corresponds to one delay or one delay cluster. But in the spatial domain, they have some unique channel vectors HL. So the proposed DDAM like this. Instead of directly transmitting the data symbol SM, here we first impose a purpose delay kappa L for the data symbol. So this is called delay precompensation because it is applied at the transmitter. Of course, it can also be applied at the receiver, so we have the delay post compensation. So let's say for the L's path, we introduce a delay compensation kappa L, and this kappa L will match with the channel delay NL. So this kappa L is just some constant value, let's say N max, minus the delay of the multipath NL. So we have the delay compensation at the transmitter side. But before that, we need to apply the so-called path-based beamforming for the delayed version of the transmitter symbol. So this FL is a path-based beamforming applied at the base station. Because we have multiple antennas at the base station, so we can apply different beamforming vectors for the delayed copy of the transmitter symbols. So this will be our transmitter signals XN. It is a vector because we have multiple antennas. And if we perform the convolution of this transmitter signal XN with the channel impulse response, we can find that the received signal YN will include 2 parts. The first part is that the delayed signal with a common delay Nmax, and it has a contribution from all the L multipaths. And the second term corresponds to the intersymbol interference. So we do not want this intersymbol interference. But because we have an additional design degree of freedom in the spatial domain, so that we can design our path-based beamforming vector FL, so that if we can remove or zero force the intersymbol interference, then it basically means that the received signal YN will be simply given by one single delay tap, Nmax. And what is more important is that this symbol will be enhanced by the multipath signals from all the multipaths. So we do not have any power degradation because we make full use of the multipath of the channel. So this is actually the ISI-free AWGA channel. But the question is that is it possible, how it is feasible to design our beamforming vectors so that all the intersymbol interference are removed? So this is possible if we have the large number of antennas. So let's say here Sn is our symbols to be transmitted. It can be the quantum symbol. And based on what we discussed just now, we apply the delay compensation. And for each delayed version of the symbol stream, we apply a beamforming vector. And this is the architecture of the delay alignment modulation at the transmitter side. But what if we do not want to apply zero forcing? So is it possible that we can still achieve so-called equalization-free single carrier communication without any intersymbol interference? The answer is yes, as long as we have sufficiently large antenna. So here we plot the correlation of the different multipath channel for the large antenna system. So HL is a multipath channel associated with path L, and HL prime is the multipath channel, or it is a channel vector associated with another multipath. So if we plot the intercorrelation for these two channels, we find that as long as the number of antennas is large enough, the correlation will approach to zero. So as long as these two multipaths have different angles. So this is actually very similar to the massive MIMO concept. For massive MIMO proposed in 2010, the key idea is that if the number of antennas is large enough, then the different users will have asymptotically orthogonal channels. Here we have the similar idea, but it is not the different users, but for different paths of the same user, we also have the asymptotically orthogonal channel. So in this case, we do not have to apply the zero forcing path-based beamforming in order to remove the intersymbol interference. We can apply the simple path-based MRT or maximum visual transmission beamforming. We can still achieve the ISI intersymbol interference-free AWG channel. So this basically shows that if we have a sufficiently large degree of freedom in the spatial domain, then our design will be very simple, which is a path-based beamforming and the path compensation. But what if we want to have a more general design? Let's say we do not have enough antenna to make sure that all the multipath channels becomes asymptotically orthogonal. So in this case, we can apply what we mentioned just now, the intersymbol interference zero forcing condition. So we want to design our path-based beamforming vectors FL so that this intersymbol interference becomes zero. So this is a condition. This is a condition for intersymbol interference-free transmission. And we will have the closed form solution for this one. And of course, we can also apply the MRT beamforming and the MMSE beamforming. But in this case, it is not per user based. It is a path based. And we all have the closed form expression. And if we consider the block structure of DAM as compared to the conventional OFDM, here we consider the OFDM, we find that the OFDM will have a CP for each symbol. So for each symbol, we need to insert a cyclic prefix. So this will degrade the spectrum efficiency, as we mentioned just now. But for our proposed DAM, we only need to insert one guard interval at the beginning of each channel coherence time. So this will significantly reduce the CP overhead, and it will improve the spectrum efficiency. So if we compare the spectrum efficiency for DAM with different beamforming techniques, let's say DAM with MMSE, with zero forcing, and with MRT beamforming, we found that the DAM will have slightly spectrum efficiency enhancement as compared to the OFDM. But this is not the key point. The key point is that for DAM, we use a single carrier transmission. So that basically means that as compared to OFDM, the PAPR will be significantly reduced, and we will show this later on. But if we consider the key concept or the key idea of DAM, actually it is very simple. The key idea is to just reduce the delay spread. So here we have the delay spread of the channel itself. We have the minimum delay and the maximum delay. So the delay spread in this case is the difference between the minimum and the maximum delay. But after DAM, we reduce the delay spread to one single delay type, here to Nmax. So this is actually an ideal scenario that we can align all the delays of all the multipath into one single delay. So that is why it is called the DAM, delay alignment modulation. But this is really a very realistic or not realistic, idealized scenario that we can reduce the delay spread to 0. In many practical scenarios, it is not possible, or it is very challenging to reduce the delay spread to 0. So what is more practical is that we can reduce the delay spread to a certain value greater than 0, but it is much smaller than the delay spread of the channel itself. So in this case, we still need to apply some other techniques to deal with the intersymbol interference, let's say OFDM or equalization. But now the effective channel has a much reduced delay spread, so we have much more flexibility to select our OFDM parameters. So this will actually motivate us to combine or integrate the DAM with other techniques, let's say with multi-carrier transmission, OFDM. So the key idea is very simple. We, at the transmitter here, we still have the OFDM transmitter processing. So we have the serial to parallel conversion to convert the different, to convert the symbol stream into parallel streams. And we can apply the beamforming in the digital domain. For each subcarrier, we may apply independent beamforming in the frequency domain. And then we perform the IDFT and to transform the signals into the time domain, and we add the CP. And this is just the standard OFDM, MIMO OFDM processing. But what is different is that we have the so-called DAM processing. DAM is applied in the delay domain or in the time domain. So here we have the similar delay compensation and also the path-based beamforming. So what is important is that now the OFDM transmitter will see a different channel after manipulated by the DAM processing. So we actually manipulated the channel delay spread by the DAM pre-processing so that we can reduce the CP overhead, or we can reduce the number of subcarriers to achieve lower PAPR. So this will actually gives us the unified architecture for ISI-free single carrier and multi-carrier communication. And we have the joint time domain and frequency domain beamforming. So for DAM processing, we have the time domain beamforming, and for OFDM, we have the frequency domain beamforming. So we have the much higher flexibility. So here is the time domain transmission signal based on the delay alignment modulation. And here we have the transmitter. Here we have the transmitter in the frequency domain. Transmitter beamforming in the frequency domain. And the received SNR will now depend on both on the time domain beamforming and the frequency domain beamforming. So we're not going to give the detailed mathematics, but the key idea is very simple. So we have the additional design degree of freedom to manipulate the channel delay spread in the time domain so that we can reduce the channel delay spread, and the OFDM will have more flexibility for parameter selection. So here we show the DAM combined with OFDM so that we can have the different selections for the subcarriers. So as compared to the OFDM, we find that DAM OFDM will significantly enhance the spatial efficiency because now the channel delay spread is smaller, so that we can use a smaller CP overhead. And what is more important is that with this delay at random modulation, the PAPR will also be reduced. For example, here we can see the DAM OFDM with 64 subcarriers, and as compared to 256 subcarriers, the PAPR is significantly reduced. Actually, the idea to manipulate the channel delay spread is not new. Even in 1990s, there's a concept called channel shortening. But previously, the channel shortening was mainly designed in the time domain based on the finite impulse response filter instead of in the spatial domain. So there is also a concept called time reversal, let's say for the underwater communications. So the basic idea is that the receiver will send a piloted signal to the transmitter, and the transmitter will estimate the delay of the channel and then do the time reverse version of the signal. So this is also quite similar to the so-called delay at random modulation. But all such similar concepts have some limitations. The first one is that they have some degradation for the spatial efficiency because they do not really make use of the spatial dimension, as in our proposed DAM concept. So for DAM, it is fundamentally different because we make use of the large antennas in the spatial domain so that we do not need to sacrifice in the time domain or in the delay domain. So we have the joint spatial and the delay domain processing, and we have the very flexible path-based beamforming, and we have the very flexible path-based delay and delay compensation. So this will enable us to achieve inter-symbol interference-free communication, even for finite or infinite antennas. So it is very flexible. But as we mentioned just now, one of the key advantages for DAM is to make use of the large antennas. But if we have large antennas, let's say if we have thousands of antennas, so the complexity, the signal processing complexity, the hardware cost of the antennas will increase significantly. So how can we deal with this issue? Actually, there are some existing techniques to use large antennas, but use more cost-effective architectures. Let's say we have the hybrid analog and digital beamforming architecture. So how do we apply the DAM in the hybrid beamforming architecture? Actually, it is very simple. Here, we still have the delay compensation for each symbol stream. And now we have the digital precoding in the baseband domain. And then we have the analog precoding in the analog domain. So the transmitter signal will include the delayed version of the data symbols, and we have the beamforming in the digital precoding in the baseband domain, and combined with the beamforming or precoding in the analog domain. So we can still design the similar beamforming architecture so that the inter-symbol interference, ISI, can be removed. So this will enable us to achieve DAM even when we have the hybrid beamforming structure. So the basic idea is that, let's say if first we remove the constraint of the hybrid beamforming, we can find the optimal digital, fully digital beamforming matrix. And then we can decompose this beamforming into the RF domain and the baseband domain so that we can minimize the difference between the optimal fully digital beamforming and the hybrid beamforming. And we can achieve the DAM for the case when we have less RF chains, or when we have fewer RF chains than the number of antennas. So here we compare the BER with OFDM and with fully digital beamforming and hybrid beamforming. We find that because we have the very few multipaths, even with the hybrid beamforming, we can achieve very close near optimal performance as compared to the fully digital beamforming, and we have the theoretical proof for this statement. And here we also can compare the spectrum efficiency of DAM as compared to OFDM and also the PAPR. And we find that the PAPR will be significantly reduced as compared to OFDM, even in the hybrid beamforming structure. So far, we only discussed the DAM in the single user scenario. But in practice, we have multi-user communication. Is it possible for us to apply DAM for multi-user scenarios? So here we consider a single cell or single base station, but multiple users. So in this case, each user has its own multipath properties. For example, user 1 may have, let's say, one or may have 3 multipaths with different vectors for each multipath and different delays. And user 2 may have different multipath characteristics. So we can write the channel impulse response for each user. Let's say for user K, it has LK multipath, and each multipath will have channel vectors HKL, has delay NKL. And based on the concept, based on the idea of DAM, the base station will transmit the signals for each user K. So we have a summation over user K. And for each user K, we also have a summation for each path, so that we have the delay compensation for each path of each user. So this is how the transmitted signal vector XN looks like for the multi-user scenario. So if we consider the received signal for user K, we find that first of all, it has one desired term with one single delay, NK max. This is the maximum delay. And again, this signal will be contributed by all the multipaths of the channel. So we do not lose any power of the channel. And of course, we still have the inter-symbol interference for this user and the inter-user interference from different users. But if we can apply path-based beamforming so that the inter-symbol interference and the inter-user interference are all zero-forced, then we only have one AWGN channel. So this is the basic idea. Whether it is possible for us to design the path-based beamforming for each user so that both the inter-user interference and the inter-symbol interference are all suppressed in the spatial domain, so that we can do very simple equalization or one single type equalization in the time domain. So this is possible if we have sufficiently large antennas. So similar to what we discussed just now, if the number of antennas is large enough, so let's say the number of antennas is much greater than the total number of multipaths for all users, then asymptotically, all the multipath channels will become orthogonal. So we can apply even the simple path-based MRT beamforming so that we do not need to do any inter-symbol interference equalization. Okay, so the details are given in the paper. Now we compare the proposed multi-user DAM with multi-user OFDM or OFDMA. So here we have the spectrum efficiency versus the number of channel multipaths. We found that if the channel of multipath increases, then the OFDM and some other techniques, let's say the strongest path-based beamforming. So for the strongest path-based beamforming, we only keep the strongest path. We discard the remaining weak paths. So we found that the DAM will have much higher spectrum efficiency because it reduces the CPU overhead and it makes use of all the multipath power, channel power, without losing any channel power. So this is the one key advantage for DAM even in the multi-user scenario. And how about the PAPR? For the PAPR, the DAM will have a higher PAPR for the strongest path-based scheme because for that scheme, it only keeps the one single path, but it has much lower spectrum efficiency. But DAM will have much lower PAPR as compared to OFDM. So far, we only discussed the DAM or in the delay domain, but we can apply the similar idea to the Doppler domain if the channel has a large Doppler spread. So here is a single user scenario in the delay and the Doppler spread channel. So here we consider multiple antennas at both the transmitter and the receiver. So we have the delay and also the Doppler for each multipath. So what we can do is that for delay Doppler alignment modulation, we can apply the very similar idea as DAM or delay alignment modulation. So the symbol, the data symbols SN will be delayed by some value kappa L, and this kappa L will be dependent on the channel delay. Let's here ML is the delay of the channel for the LS multipath. And the additional term is the Doppler compensation. Because we know that a constant Doppler will introduce a linear phase rotation. So here we can apply a linear phase rotation for this Doppler. So here, let's say if we can apply, estimate the Doppler of the path to be nu L, then we can apply this Doppler compensation. And of course, we need to have this path-based beamforming so that the received signal at the receiver will include two parts. The first part is one single delay M max, and what is more important is that it has the signal contribution from all the multipaths, and there's no Doppler because all the Dopplers have been perfectly aligned or compensated. So this is the desired signal with time invariant channel, and it is a time non-dispersive, and we have the ISI intersymbol interference. But now, again, if we can design our beamforming vector, beamforming matrix at the transmitter and the receiver, so that this part becomes 0, then we do not have intersymbol interference. And this is possible if we have large antennas. So here is the architecture for the DDAM. We have the data symbols SN, and we apply different delay compensation and the Doppler pre-compensation. And then after apply the path-based beamforming, we sum them up and transmit over the base station antennas. So we can apply the similar processing at the receiver side, let's say in the uplink. So this is the receiver side DAM. So the received signal will be like this, right? So again, if we have the large antennas, asymptotically large antennas, without having to apply the zero forcing beamforming, we can still achieve the intersymbol interference-free communication. And this has been proved in this paper. If the number of antennas is large enough, DDAM can achieve ISI-free and time-invariant communication with a very simple path-based beamforming and the delay and Doppler compensation. So if we take a look at the channels at the different stage of the DDAM processing, we can understand why DDAM actually is feasible and it works in 6G. So here, if we consider the antenna, so here, this is the antenna. If we consider the channels seen by the base station antenna, we basically experience the channel delay and Doppler spread given by the channel itself, because we haven't performed any manipulation to the channel. So this will be the channel as we discussed just now. The delay spread and the Doppler spread can be large. But after the path-based beamforming, we can actually decouple the delay and Doppler in the spatial domain. So let's say in this first pass, with this beamforming matrix F1, with zero force, all other multipaths, we only see the first pass here. So this is just one single pass. And similarly, pass 2 and pass 3, they are all decoupled in the spatial domain. So we can see a channel with just one single pass. So with this one single pass, we can apply the compensation in the Doppler domain and the delay domain, so that we can shift this delay and Doppler to any desired location as we wish. So for example, we can apply all the delay and Doppler compensation so that all the delay and Doppler locations will be aligned to this single path, single location. So actually we achieve the delay and Doppler alignment. And this is possible, as we mentioned just now. This is only possible if we can decouple the different delay and Doppler multipaths in the spatial domain. So that is why we need to make use of the large antennas. So in this case, after DDAM, the channel will become frequency non-selective, and it is also time invariant, because we have transformed the delay Doppler doubly selective channel into one single delay type in the ideal case. Of course, in the practical scenario, we may apply DDAM with OFDM, and so that we can have a more flexible design. So here are the mathematics for the DDAM. I'm not going to give the details, but the key is to understand the concept or the key ideas for DDAM and why it works, and why it only works in 6G when we have large antennas, when we have multipath sparsity, when we have integrated sensor and communication, so that we can estimate the different delay parameters, different multipath parameters. Here we compare DDAM with different OFDM techniques. Again, we find that it can achieve higher spectrum efficiency and also can similar BER performance. And what is more important is that it can reduce the PAPR, because we may have more flexible parameter selection for OFDM. Okay, so we have performed one very simple prototyping for DDAM. So here we consider a very simple scenario where we have two paths for the base station and the UE channel. So in this case, we can apply the channel estimation or the sensing algorithms to estimate the delay and the angle of the two paths. So in this case, let's say the base station will transmit the channel sounding signal, and the UE will estimate the delay of the two paths, and then the base station will calculate the delay difference of the two paths and to perform the delay compensation. So the base station only needs the delay difference of the two paths in order to achieve the delay alignment modulation. And here is the experimental result, which is the result for the delay. We found that, okay, we have the two very clear delay clusters in the delay domain, and we can apply the what we call the delay alignment modulation to align these two delays. So here is a constellation without delay alignment modulation. So on the left-hand side, we do not apply delay alignment modulation. So the constellation is very messy. So after delay compensation or after delay alignment modulation, we have a very clear signal constellation. So this is the actual measurement result, the experimental result for DAM. Another technique to reduce or to remove the intersymbol interference with multiple antennas is to only use one single path. As we discussed in our simulation result, we only keep one of the single paths. So here on the left-hand side, we use only path 1, and we completely remove path 2. Similarly, we only use path 2. So we find that if we only use one path, the SNR is very small. But if we can use 2 paths with delay and amplitude modulation, we can achieve better signal constellation because we have higher SNR. We make use of the signal contributions from both signal paths. So that is why we need to apply delay and amplitude modulation. So DAM is actually quite suitable for ISAC. So as we mentioned just now, for ISAC, the main purpose is to extract the path information. And another motivation to apply DAM for ISAC is that DAM can have lower PAPR. So it basically means that given the same average power, if we can make use of DAM to reduce the PAPR, that means we can transmit with a higher average power. So that is the definition of PAPR. So this makes DAM especially suitable for ISAC. And if we consider the ISAC for different waveforms, let's say for single carrier FDMA, OFDM, or even the radar-centric waveform, let's say FMCW. So they all have different limitations, for example, in terms of the PAPR, in terms of the receiver complexity. But if we apply the DAM, as we mentioned just now, so we can apply the delay increase the subcarrier spacing so that we can have more robust to Doppler frequency shift. So this will help us to further enhance the performance of integrated sensing and communication. So in this case, we need to design our per path based beamforming. Let's say we want to maximize the communication SNR, and we need to ensure that the intersymbol interference is suppressed, and we need to make sure that the desired targeted direction will receive the minimum SNR, and we also want to make sure that our peak side lobe or integrated side lobe is below a certain threshold. So we can formulate such an optimization problem. And here is the beam pattern for our proposed DAM. And we found that the signal will be pointed towards both the communication user direction and also the directions of the sensing target. And we achieve the intersymbol interference-free communication because all the different multipath, they will have orthogonal channels after this zero forcing. Okay, here we compare the PAPR in the ISAC scenario. We find that the PAPR of the proposed DAM is much smaller than OFDM. And we also compare the RMSE of the velocity. We find that our proposed DAM will achieve much smaller RMSE for the velocity estimation because it has it can enjoy more flexibility for the subcarrier spacing. But for OFDM, because of intercarrier interference, then the velocity estimation is very poor. Okay, so this is how we apply the DAM for ISAC. So in this talk, we introduce the concept of DDAM, or delay-Doppler and amplitude modulation. And it is motivated by the intersymbol interference mitigation techniques when we have large antennas, when we have multipath sparsity, and when we want to apply integrated sensing and communication so that we can distinguish the different multipath channels. And we try to highlight that DAM is not trying to replace OFDM. As we mentioned just now, DAM and DDAM can be naturally combined or integrated with OFDM, and also even with OTFS or whatever equalization techniques, because the key idea is that with DAM or DDAM, we try to reduce the channel spread and the delay spread so that whatever systems or OFDM system will see a more effective channel with reduced delay and Doppler spread so that it can have more flexibility for the parameter selection. Let's say for the selection of the CP overhead, for the selection of the number of antennas, and so that we can have achieve lower PAPR, higher spectrum efficiency. Of course, there's no free lunch because we need to have large antenna. We need to estimate we need to distinguish the different multipath. So it is not sufficient to do the channel estimation in the time frequency domain. We really need to separate the different multipath. So which is exactly what we want for ISAC. Okay. So here are some references. And with that, I would like to thank my collaborators and also my students, and thank all the audience. Okay, that's all for my talk. Thank you.
Thank you very much, Professor Zheng. That's a great talk. Thank you for your great idea on this DDAM, which I personally enjoy listening very much. I hope you wouldn't mind that there are some questions from the audience that you can, if you have time, I hope you wouldn't mind answering them.
Sure, it's my pleasure.
Thank you. There are several questions, and I'm trying to group them into different aspects. I think the first aspect is about the comparison, especially with OFDM. For example, you have mentioned in one of the slides that OFDM requires overhead, which is mainly due to CP. But our audience were questioning whether the overhead of DDAM, I mean, from the antenna domain, need to be taken into account. Do you have a comparison with the same number of antennas, CP or in general overhead, comparing DAM and OFDM?
Yeah, that is really a very nice question. Yeah, the something here is that the DAM will only require one gap interval before the channel changes. So for the channel coherence time, actually even more relaxed scenario, when the so-called channel state information or let's say the path delay or the path vector before the path delay and the channel vectors changes, we only need to have one gap interval. But for OFDM, we need one CP for each OFDM symbol. But as the audience mentioned, here we do not really consider the overhead from the antenna domain. But based on my understanding, for the antenna domain, the antenna domain will kind of affect the spectrum efficiency from two perspectives. For example, for the beamforming gain, right? If we have more antennas, we can achieve higher beamforming gain. And another one is the spatial multiplexing gain. Antennas is much larger than the number of multipaths, so that will not be a big issue. So if we want to, let's say, consider the same number of antennas, that is really a good question, but we really didn't consider this. Let's say if we have 5 antennas and 5 multipaths, maybe my guess is that the DAM may not have the so-called advantage in that scenario. So that's why we need to consider it in the massive MIMO or XL MIMO scenario. Yeah, but I think that is a good question, a good point. Yeah.
Thank you. The second question is related to the designs, especially when you are mentioning that DAM and there are some similarities between DAM and the channel shortening. There's one question from the audience asking, do you consider that DAM is a special channel shortening scheme with a constrained degree of freedom, especially when we are talking about time domain equalization here?
DAM, I think DAM is indeed one type of channel shortening technique. If we define the channel shortening to be the technique to reduce the delay spread and the Doppler spread, yeah, that is indeed DAM is one kind of method to reduce the channel delay and Doppler spread. But here, as I mentioned just now, the channel shortening was studied previously, I think maybe 30 years ago, 20 or 30 years ago in the time domain, because we have the very similar idea to apply the finite impulse response filter Actually, this is also like a equalization. So if we wanted to define equalization like this, this is kind of equalization. But what is most important is that we need to use the spatial domain so that we do not sacrifice or we do not bear with the same complexity as the time domain equalization, because for time domain equalization, the complexity is a big issue. But if we can perform this kind of equalization or channel shortening in the joint spatial, delay, and Doppler domain, the complexity could be significantly reduced because we simply have the delay and Doppler compensation and the path-based beamforming instead of the more complicated equalization design. And again, so there are similarities, but there are new opportunities for us to make it more feasible and more effective in 6G when we have more antennas, when we have channel sparsity, when we want to do ISAC, we will try to estimate the multipath parameters. Yeah.
Right. Thank you. The third question is related to the channel state information. And it appears to us that in order to make DDAM work well, we need to have a certain level of accuracy in the CSIT. The audience are wondering, what is the most practical scheme to have the CSIT for DDAM transmission, and how robust it is against the CSIT era?
Yeah, I think this is really a very good point, but we didn't discuss the channel estimation due to the time limitation. The short answer is that the CSI requirement, the channel state information requirement for DAM, I think match exactly with sensing or ISAC. Because let's say if you want to perform the ISAC between the base station and the UE, so this is so-called bistatic ISAC, then we want to resolve the delay. We want to estimate the delay. We want to estimate the angle so that we can know the distance. We can know the direction of the target. So this is exactly what we want to achieve for channel estimation in DAM or DDAM. Of course, just now I forgot to mention the Doppler because we also want to estimate the velocity. So the key idea is like this. What we can do is we can perform whatever sensing technique, let's say in the joint spatial, delay, and Doppler domain. It can be the super resolution techniques, let's say by using music. It can be based on IFFT, because in the spatial, angular, and the Doppler domain, they can estimate it in a decoupled way by applying FFT and IFFT in the subcarrier domain, in the symbol domain, and in the antenna domain. So we can have the delay, Doppler, and angular cube like this. So in that case, we can apply the DDAM. So because we can separate the different multipaths in either of the domains. So of course, we do not try to estimate the perfect channel, even with imperfect channel estimation, just like in sensing, it is still possible, because that is why we propose the so-called DAM or DDAM with OFDM, because that we may introduce some residual intersymbol interference, but that can be handled by OFDM or OTFS or some simple equalization, maybe 2-type or 3-type equalizations. So that will significantly reduce our channel and delay spread and make us enable more flexible parameter selections. Yeah, that is the key idea.
Okay, thank you very much. And I also have personally a follow-up question, especially also related to the channel estimation aspect. For example, if we are considering a high-speed train transmission where we want to make a reliable communication, because the high-speed train is not only because of not only in the presence of Doppler, but it also has this quick change of the scenarios. I wonder if a DDAM, or in general this idea of using spatial domain degree of freedom to mitigate the interference will work in such case where the actual environment is changing significantly.
Yeah, that's a good point. Yes, indeed, the high-speed train, we have the high Doppler, but we have the fast variation of the environment. Yeah, we frankly, we haven't considered that scenario yet, but I think if I want to answer this very shortly, maybe the key idea is that the environmental change, maybe you are considering whether the the angular or the spatial information will
Yes.
also vary as
Right.
the chain goes by. Yeah, I think that is a good point. But again, this is quite similar to sensing, right? Because for sensing, we also need to track the high-speed target, and we want to estimate the delay. We want to estimate the Doppler. We want to estimate the angular. So as long as we can do sensing in such a scenario, there should be no problem because we can have the tracking mechanism. Let's say we can do the tracking by using, let's say, the common filter or extended common filter, so that we can tracking the not just the tree itself, but also the scatters in the environment. That could be possible, but I think there should be more work to do in this more challenging scenario. Yeah.
Yes. Thank you very much. I think that's all the questions I have so far collected. And I would like to thank you again for the great talk and your nice answering to the questions. And I hope
Thank you
I hope
very much.
everybody
Thank you,
enjoyed this
Tanya,
talk.
and thank you all. Thank you all the audience. I'm sorry for my internet connection.
It's okay. It's okay. We got
Okay.
your idea most, so
Okay,
don't
thank
worry
you.
about it. All right. Thank you very much, and see you guys next time. Bye bye.
Okay, bye bye. Bye bye.
Bye bye.